Okay, so I need to move forward here. I'm still kind of waiting for Floyd 4 to reboot at this point, but I'm going to go to Floyd 1 at this point. So again, we are moving to just pure CPU time and multi-threading. So I've got this code2.f that was my main bread and butter application, Fortran code. I'm just going to try a module avail to see what I got here. And I do like the, oops, I got a paste accidentally in there. And there were errors on that UV dump, but the power reset took care of things. But again, for both of you, it's useful to check the BIOS output on the blade that had the CAD error to see if there's anything there as well. For example, sometimes during boot, if you've got more than one base I/O, it might fail on that. Or hardware errors or things of that sort. So you got to watch for that. So I'm going to do a module avail. And I do have a Intel. Have you tested this, Brian? iFort. Okay,
yeah,
so
I mean,
iFort, huh?
I mean, yeah, I did the lab yesterday.
Yeah, I'm just checking.
Yep.
Okay, so I'm going to do an iFort. I'm going to go -03 for highest optimization. -O, code 203, code 2.f. I'm trying to get my baseline again. I did have CSA accounting. Did you install CSA on this, Brian?
I did.
Oh, good. Let's see if it's working then. But I'm going to do a time /code 203. You know, all that task stat CSA data, I don't know if anybody else is actually using it. I don't know of any tool that can actually get out there and get to it in a productive way. Let's run this and see where we are. So this one's coming out in the 9-second range. Again, I could run it multiple times just to see what kind of variance there is. I would want to run it 5 to 10 times, something like that. That's good enough for me. I'm going to do a CSA COM-N code 2. And here I can see all the different code 2s. Again, some of them were in the 130-second range when we were just using vanilla. Again, I did some of this PBS as well. And here we were in the 12-second range, 10-second range. With the GNU compiler 03, it's in the 20-second range, but there we got to 25. Here was one that was 156 seconds. And again, this is the same calculation, same program. Now, here's what happened, Brian. File system full condition. So I'm going to do a CSA run and clean that up. Oops. This one thing is I like to get temp and var temp off a root. And a lot of sites leave temp and var temp in the / file system, making it easy to attack that file system and fill it up. So let's see if CSA COM is working now. Okay, I don't have anything there. JSTAT. Do have a job ID. You'll see. There's still nothing in there. Permission denied. Things can get out of sync. I wonder what that thing is. That was a while ago at 10 o'clock. I'm wondering if we went through a memory event here. Rep-I kill var log messages. So we did have some kill events, but not today. That was the 12th, it looks like. How long have we been up? We've only been up a day, so those don't look relevant. Let me do a D message, grep for a kill. No kills since the current boot. Okay. PS-E, grep for syslog. I was just expecting a little bit more in the syslog. And I got this traceback that we'd done earlier when I had done the echo T in there. That's what that was from. Okay, I'm not sure why I'm not getting anything right now. Service, CSA, start. There we are. Check config. My lab might not have done this, I don't know. Oh, it is on. So for some reason, I don't know why it wasn't on at the time, but at least now I've got instrumentation going. Okay, let me get out of here. JA will also start stuff. And a JA-S, for example, will give me a summary. I haven't done anything yet, but now I've got instrumentation in place. So let me do that thing again now. Okay, CSA com-N on code. There it is, and again, we're in the 9-second range. Okay. Now I want to profile it. I'm going to do a perf record. I think that's how I'm going to do it. Oops. This is by default saving the samples in a perf.data file, but you can use a -O to change the output file that it's writing to. So here we got 16,000 samples. We looked at the program counter almost 16,000 times, got 1/3 of a megabyte of data, and again it wrote to perf.data. So now I'm going to do the perf report, and it's defaulting to perf.data. And once again, my main work is in CLint, but I am seeing the equivalence where two arrays are being equivalenced, and that's a copy type of thing. And then I see state and step, and the rest of these I don't care about. So most of the time was spent in CLint. Stop me if there's a question. Trouble here is I can't get down to a line number. Let me, I should have done this. I4 here, yes it is. I4-G, I need the symbol tables, -03, -O, code 2, 03. So now let's run that thing again. Now one trouble here, perf is owned by root. It's not really for end users. I don't know why or whatever, but root permissions aren't always there. Let's see. Okay, so that worked fine. Perf report. And again, I only get down to a subroutine name, not to a line number. Oh, look at this one too. Intel fast mem copy. So these are the Intel libraries. Intel memset. The clear page is causing an allocation here for memory. And then you can also spot the kernel time here, the system time. Spin locks. I was looking for that one that we were seeing before with the IRQ, spin lock IRQ save or something. I'm not seeing it right now, but that's okay. So I can't get down to a line number. So let me try now do a module load perf suite. See if psrun is in my path. It is. And we have both a ready-to-use untarable perf suite, but there's also the source. And for both of you, hang on a second. I'm checking the latest version that I just heard about. And let me put it into chat. 1A5.1. So it's a 1A 5.1. And what did we have here? AA4. So there's a 5.1 version that I need to get to, but I'm not going to worry about that right now. And in that 5.1 version is this show event info. That's something I was also looking for. SW,
Yeah.
Perf Suite.
Speaking of what's it called, versions of software, on Floyd 2, there's an old set of compilers. It's
Okay.
11. It's not the 12.1.
Yeah, I'm not.
Is that what's supposed?
I'm not going to worry about that right now. I'll check it here. I'm not. Let's see. I4-V. Yeah. So this is a 12.1 compiler that I have here. And it was this tarball here for this 2011 SP1 tarball. I found that in Home Guest Intel. So this is what we were using. But I'm not going to worry about the rev level at this point. We can take a look at that offline, okay? Does that answer your question for now? So I've got this program. I'm just going to do a ps run /code203. One thing I don't like here is I have to figure out what the file is that it generated. I usually do like an ls-lt if I'm in batch or something like that, and then grab the one that was just generated. So I'm going to do a ps process on that file. And I do have symbol tables on, so now I can actually get down to the line number. So again, there's CLint that we saw in perf top or perf report. There's the mem copy, there's the state. And again, as I said yesterday, state has got this equivalence. No, I'm sorry. We have the system library routine that's doing the mem copy and Intel specific mem copy because of equivalences that are occurring in the source. But then state is the next thing on the list. None of these are CLint. 1, 2, 3, 4. Down here is where CLint starts. But it's at the top of the list here because it's got lots of little samples that all added up to 606. And then 157 times we were in the mem copy, and 97 times we were in state, and 47 times we were in step. So I'm able to get to a line number here. Any questions right now? I want to go one step further here now. This time I'm going to try a -C. Oops. And let's see if this works. And that's not working for some reason. I went through this yesterday as well. Let me try this again. I had it working on my system. Let's just see if LS works here. Module load perf suite. Might even be a module file problem.
I mean, I did the labs with certain ones yesterday.
Yeah.
And I didn't use the.
You didn't do the Perfex one, did you?
I mean, I was doing TS runs. You're not still out of disk space, are you?
No, but I'm trying to use the Perfex report, which is going into hardware counters differently. But I'm not sure why I've got that DSO problem. Let's just see if I get it now. So that one worked. And I'm not sure what's going on here, Brian, but it was almost like when I'm root it worked, but when I was an end user it did not. I don't know what was going on there. So let me see what happens now. Instead of doing an ls, I'm going to do my .code 203, and that one's working. So this is what I found last night, and I haven't dug into why root is successful, but no one else is. It might be something to do with permissions on the interface to get to the hardware counters, the TCL interface or something. So it does look like that successfully ran. So I'm not going to do a PS process on that thing. And now I'm actually getting into hardware counters. So that's why I was trying to get the Perfex report working. But why I can do it as root but not in users, I don't know yet. So it's telling me all about the system, the CPU characteristics. And then here are my hardware counters. So this is just the line number. I don't really care about that, but I've got like 32 counters. Here's the description for it, and here is the raw value for that counter. So some of these are bad. For example, TLB misses. This one right here, if I'm tuning, I'm going to want to trap on TLB misses, find out where I am in my program, and see if I can reduce them. So each one of these things is a particular hardware counter. Now, show event info would show me all the hardware counters I can get to. And I'm not worried about this one right now, no description available, but I do get numbers here. These are single point, floating point operations, or single precision, double precision, and vector operations. And then it's showing me the actual PAPI event that we're trapping. So I had 32 counters that I could look at once. And that multiplexing says I could look at them. And then we get some derived statistics for the experiment, including cache misses and megaflop performance and things of that sort. And again, it was down in the 9-second range, 91%. The rest of the time was this 0.8. Must have been sleeping or something. It doesn't know what happened during that 0.873 seconds. Might have been a startup and shutdown of the perf suite experiment. Now, do we have a matrix here? No, that's okay right now. So, I've got two experiments now that give me line numbers and hardware counters for my baseline. So now I want to multi-thread this thing. So I'm going to do iPort. Now, the rule in my class is, this is administrative classes, we can't change the source code. But there's still a lot of things you can do to identify problems and work with application programmers to optimize their program. That means reduce cache misses, reduce TLB misses, reduce instruction pipeline flushes, all that sort of thing. Okay, so I'm going to do an iFort-03-G for symbol tables, -parallel. This is invoking a preprocessor that will automatically multi-thread my application and stick in OpenMP directives for me. Intel bought the assets of Cook Associates that was also something used in Cray days to do multi-threading and what we used to call auto-tasking, to automatically multitask it. Trouble is here in this release, you can't save the intermediate file. So in the older MIPS compilers, for example, I could save off the intermediate file that had the OpenMP directives added to it, and then I could go in and adjust it from there. But here I can't. There's no intermediate file. Let me do a -O code 2MP, code 2.f. Now this is going to use p-threads underneath. There are basically three types of threading: p-threads, OpenMP, which calls p-threads, and then MPI. So let me do a time./code2mp. I got a problem here. And I hit this yesterday too. Not sure what the problem was, but when you see this, this is the OpenMP library from Intel. Okay, not coming back very quick. Remember, we were at 9 seconds before. Let's get onto the system here. Bring in top. There's my code 2MP running. Finished. Okay, the elapsed time of that thing was now 37 seconds. Well, wait a second, we were just at 9 seconds. And now, the amount of CPU time that I used was 19 minutes, 23 seconds. Let's run that again. And I had 38 seconds of system time. Go back to here. So I do have system time coming in now. By the way, watch this WChan here. We're going to see a Qtex system call here. Waiting, waiting. Come on, show me one. It may finish. Notice, by the way, look at my percent CPU utilization is now greater than 100%. And in the latest tops, the maximum it can go to is 999,999. And then it will truncate. Okay, we never saw that. That's okay. So again, 19 minutes. So this isn't looking too good for me. I want to try to get shortest repeatable elapsed time. Now, when you see it greater than 100, it's probably pthreads. And in order to see pthreads, I am hitting a capital H, a Shift H within top. And now it says show threads on. And now I can see each individual thread. We did see an anomaly there for a second. So I can see all these code 2MPs running. And let's do something else here. PS-E, rep for code 2. I only see one there, but if I put in a dash capital T, oh, it's finished. Let's run it again. Still in the 19-minute, 37-second elapsed time. So by using a dash capital T, I can see it on an individual thread basis. And I'm getting 33 threads. And if you look at these threads, the second thread here is a shepherd, is a sleeper. That is not a worker or part of my program. The Intel compiler spawned that thread. And again, a topology shows I've got 32 CPUs. So by default, the Intel OpenMP library spawned a thread for every CPU I got. And just because I'm getting more and more threads does not mean I'm getting more work done. Let me run this again. So let me go back into this one. So there's all my threads. And again, the second thread is not part of my process, not part of my work. And we got to make sure we don't pin that thing. We got to skip that thing when we get into placement. Again, I got 33 threads, 32 CPUs plus an extra thread. The second thread spawned off is from the Intel libraries. Go back to top. I'm going to do a capital H. And I can see each of these individual threads. Again, there was the anomaly I was talking about. And that's done again. So let's profile that thing. Let's do a perf report. First of all, let me remove the perf.data that we got. Perf record /code2mp. I'm not so sure how well this is going to handle multi-threading. Normally I would attach to a single process, but let's see what happens here. When you get into multi-threading, PS run and perf have to be a little bit more aware of what you're trying to look at. Now remember, we were in the 9-second range and sealant was the top of our list. By the way, let me get at this point I need to get a remote desktop going here. Oh, I don't seem to have, oh, there it is. And at this point, the main reason I want my remote desktop is for PMG sys. Waiting for my not really getting a response out of it right now. What's going on here? I don't see anything wrong there. There we are. So again, I got a 32 CPU system, and Intel is automatically spawning up 1 thread per CPU. Before we go on, let me do a perf report now from that one sample. And now, look at what's at the top of the list. 50% of the samples I got were in the OpenMP, Intel OpenMP library. And it was in a routine called KMP wait sleep. Underscore means it's a internal subroutine. Sealant down here, third in the list, was only 7% of my work. So I got 50, 60, 70, almost 80% of my samples were in non-productive Intel library routines. And by the way, we can also see, I talk about p-threads with a join, p-thread join type of thing. This is the point where they're trying to synchronize and wait for all the individual threads to finish. And like I said, there were 2 types of synchronization. This is a yield situation. So I sit there saying, are you done, are you done, are you done? No. Then the KMP libraries will do a sched yield, and then we're sitting here waiting, spinning, waiting, saying, are you done, are you done, are you done? And we can even see the sched yield here. So now my program is spending most of its time in a synchronization event, communication overhead. That's what OpenMP Intel library OpenMP communication looks like. That's non-productive work. Okay, I can sit there and make this program spin for a month. It will never finish, and it'll be 100% CPU utilization and no work getting done. Let me do this again, perf.data. Run it again, and I want to go back here. Look at the system time that's going on in here. And that system time, let me see if I can catch it here, perf top. And it has to be the kernel, is the CPU scheduler. All that system time there is thrashing on a sched yield. We can even see the yield being made here. And most of this is not productive. I've got 6% of it that's actual work. Waiting for it to finish. Oh, finished. Let me quit out of there. Now, I'm going to do a man on sched underscore yield to the whole purpose of sched yield is to give up the CPU. so that somebody else can use it. A sched yield is going to result in a context switch. Context switch to share that CPU with something else. The trouble is there's nobody else to share it with. The other thing that's going on here, man, Futex, the Futex system call is my check. So basically the Futex is, are you done? Are you done? Are you done? Are you done? And that shows up as user time. And then it says, oh, I've tried you often enough, I'm going to yield the CPU and give you a sched yield. So Futex is the checking, the synchronization event, and then the sched yield is to say, let somebody else have the CPU instead of spinning on it. Intel, OpenMP, and Intel MPI do yields. SGI's MPT does a spin. Now I'm going to do something bad here. Export OMP underscore num underscore threads equals, oh, let me go 512. Now I'm going to run that thing again. And look at what I got going here now. Let me bring up top. And this is easy to find at sites. So there's that Futex wait I was talking about. But look at my system time is 80%, 85% on the system. Let me do the top sys. And all that system time is basically the CPU scheduler doing context switches. So all these code 2 MPs, 80% of the time they're in the kernel doing something. Again, I'm going to do a perf top here. Oops. And again, both of you, perf top is dangerous on anything other than these last couple of kernels. SLES 11 SP1, perf top is not safe. It can deadlock your system, and not even an NMI can break it out. So look at my system time now. It's all thread return and CPU scheduler.
But the new perf top will allow us to do it on a 2000 core machine?
Again, I would be careful and start attaching to an individual PID. But if you're SLES 11 SP1, don't use perf top. Use perf top-P.
Right. But when we do move up, is this something we can do or something we should avoid?
No, it's been fairly safe. I haven't tried it on a 4096 CPU system yet. What has happened, though, overnight, for example, I did drop into KDB and had to type a go. So when I'm using perf top, I try to attach to a particular PID or get out real quickly. And I'm safe right now. I'm just trying to – the trouble is the intensity of the interrupts, and it loses an interrupt. And I got dazed and confused messages. Let me grep dazed. /var log messages. No dazed and confused messages there. If I'm running multiple perf tops, which is what I did last night, I basically fired up 5 perf tops. And there are options in perf top to slow down the sampling. Event period to sample, you can slow down that. You can attach to a particular PID. The default was all CPUs, and that's the problem. Slow it down for a number of seconds between refreshes. Sometimes you do have to change the number of pages mapped. Sometimes perf top will say you need more mapped pages or something. Attached to a PID or a thread. That's pretty much it. Now, that program is still running. Can't even see it here. There it is. Do an H. There's the are you done, are you done, are you done? I was trying to see some sched yields. There's the synchronization. There's synchronization. They're not all synchronizing at the same time. We used to call it gang scheduling. They're not all being connected at the same time and saying, are we all here? This is a party line. Let's get done with this piece. So this program's been running for a while now, and I can set this up to where it will take weeks for that 9 seconds to get calculated. Now, in the process here, I'm going to do a star-W, pipe into more. And typically on this system, the number of context switches I was doing was in the 200 range. Again, a context switch is swapping something off the CPU and putting something else on it. The sched yield is designed to force a context switch. Look at the context switches I've got going on now. Now, I'm going to do a PS-ET pipe ref for code 2MP. Oops. I was getting the environment information, which, by the way, can I catch it here? It's kind of hard to read without the carriage returns in there. I'm looking for the environment variable OMP num threads, but it wasn't in this window anyway. So let's take a look at this one. Okay, there's all those code 2MPs, WC-L. You got 513 of them. Let me go into proc 7284. That's the parent thread. Okay. Let's just see cat wchan. Mutex wait Q. That one was in a mutex situation here. Now also in that directory is a task directory. If I do an ls on task, I'm going to see the thread IDs for each one of those threads. And the other thing I want to do here now, I'm going to cat env. Oh, what is it called? Environ. Cat environ. And the problem is, if I can find it here, I've had this happen out at sites when they're doing OpenMP MPI hybrids. And they may say I'm on a 512 CPU system, so they spawn off 512 threads with MPI, and then it linked in an OpenMP library by default, which then spawned off another 512 threads and overcommitted the machine. And here's my problem right now. I've got more threads than CPUs. We are thrashing on synchronization overhead. And all of that system time is from these sched yields that are causing the CPU scheduler to go crazy. Let's do an strace-f on that PID 7284. The F says follow children. And there we can see all the futexes from the parent thread and occasionally a sched yield. Let me try another one on an individual thread. Let's go 7796. And there's the futexes and the sched yields again. Looks like it finished now. CSA COM-N on code 2MP. And that one took 473 seconds. You're going to see one thread or one entry per thread. I'm just trying to go up. I had 515 of them. And I also am looking for the last thread. Let's try that again. Trying to find the shepherd. There it is, right here. By the way, I can get PIDs out of this stuff too. Dash P. Put it into X. Oops. Why did it do that? Thought I'd get some IO redirection, but it's treating that as a file. So here I can get the PIDs here. So there's all the threads for that one multi-threaded group. I'm going back up here again. Oops. I need to jump through this more carefully. Trying to get back to the beginning. There it is. Huh. I'm looking for the shepherd thread and not seeing it here. This is a shepherd thread from something else because of the time window that it was running. But it has no CPU time associated with it. Okay. Yeah, I'm not even seeing it here. Here's the one that I was looking for. There's the shepherd. So, try this again now. So I want to do a PS run, dash P to follow P threads. And then I'm going to do my code to MP. Now this one I don't have OMP num thread set high, so I should not, oops, module load, perf suite, also, oops, source. Intel-12.1. Now let's see if I can run it. And I do see a lot of system time in there. Let me break out of there. Echo $OMP underscore num underscore threads. Not set. Okay. So let me set it. Export OMP underscore num underscore threads. Let me go just 4 threads wide this time instead of 32 and see what happens here. Still seeing a lot of system time in there. Bring up top. So I can see the code to MPs. My system time is 10% or so, 70%, bursting back and forth.
Why is the CPU time, what's it called, 3100?
I'm sorry, what was the question?
Why is the percent CPU, what's it called, 3100?
No, good. Because they're multi-threaded, so all the threads, OpenMP and P threads, will not show up in top by default. So if you see that greater than 100, there are things running concurrently. So if I do an H, that will expand that and then show the individual threads of that thing. And now we should be, after we get the sample, now we're down to 100 on a per thread basis. I'm going to do H off again. PS and top will not show threads by default. So I had to use a PS dash capital T. Okay, it's finished now. So again, when it is running in parallel concurrently, any pthread type of application that they're running concurrently at the same time under that parent, you don't see unless you ask for it with the H option. Does that answer the question?
Yes.
So that's a good indication that it's multi-threaded, that there's some pthreads going on in there. MPIs will be separate processes. They're not threads, they're separate processes. So let's just take a look at this now. Yes. And look at, I got one per thread. Each one of these individual threads has its own experiment report now. So I'm going to do a PS process. Let's just pick one of these. And like we saw with perf top and other things, this is all the Intel library stuff, doing the are you done, are you done, are you done? If not, sched yield. Here's the libraries doing the sched yield. Here's the barrier itself. And here's our sealant. It's down at 4 samples, only 0.3% of the time that we collected on this individual thread was in my worker. Now, I'm not liking something here. I thought I said it. Let me do an export. Okay, oops. OMP, I'm sorry. My mistake. That's not set either. Export OMP underscore num underscore threads equals 4. Now let me run that experiment again. Here we are. So here again, we're going to see it bigger than 100. Well, let me get out of there on a threads off. And here you can actually see that we're basically 4 threads wide when we're at 400%. System time isn't too bad. Let's see if I can catch this up here. Oops. And I don't like the placement here. But now I'm only 4 threads wide. Excuse me. Finished. Let's see where we were. I'm just going to pick the one thread here. And perf could not get down to a line number, but here we can. Same sort of thing. Where are we on time for this thing? So we're still in the 30, and here's a group here now. So you can see I went 4 threads wide plus that shepherd sleeper that I was talking about. Again, the same program, single threaded, is 9 seconds, but now I'm at 38 seconds wall clock times 4 CPUs, 160 seconds instead of 9 seconds. So my CPU utilization has gone up, but my throughput has gone down. Okay. If I do my star-w, oh, I do have a corruption here. That's just got to be a throwaway. Ooh, we got a corruption of the system file. When the file system full condition occurred, I corrupted my data. So let me just remove SA18. I'm going to fire off the single one to get a start of it. Let me do another one here. Type in SAR. At least I've got data coming back now. I've got all these XML files now on a per thread basis. I'm not sure I want any of them right now. I'm going to remove all the Code2MP XML files. Good enough. So now let me try this again. I'm going to do something else here. First of all, PM chart. Put it in the background. I'll look at CPU utilization. Good enough. Let me just echo $path to see what I got. I'm going to do that. I don't see the Intel compiler in my path. I'm going to do a module load Intel-12.1. So /code2mp. I could probably be running it under time. So look at now, right now is running fairly cleanly, mostly CPU utilization. But again, that's not productive CPU utilization. Again, we knew this thing was at 9 seconds. I'm going to do it H. So we can see the 4 threads. Again, the 5th thread is not going to show up here because it's not running. Okay, that's finished. Let me do a SAR. We didn't get it long enough. Let me run it again. Remember, SAR-W1-5. My context switches are in the 300 per second range. Let me run this thing again. So we're up in there, but let's do a SAR-W. Not bad. I'm in the 600 per second range. I'm going to do that export OMP_num_threads again. Let me go 128 wide this time. Oops. Sometimes people put this in their login environments to make it easier. Let's fire this thing up again. Okay, so there we are. I'm going wider thread count here. You can see all the system time associated with it. And I'm feeling the impact of this as well. My desktop is slowing down here. And look at all that system time there. I'm actually a little surprised. I thought it would be higher system time. How many threads did I get? PS-ET, grep code 2. Let's pipe it into WC-L. 129. Huh. I'm a little surprised I'm not actually getting everything going here. Now watch. /code2, let's do a time here. and run that same program single-threaded. You can see it here on the CPU up here pinned down. Anyway, yesterday I was seeing a lot of migration threads. I'm not seeing them today. Okay, so that one came down in at 14 seconds. What's going on here? It's still running. Something's still running. Oh, the code 203 came in at 14 seconds. It got finished before the multi-threaded version did. But again, we know that that thing can get down to 9 seconds. So that's 6 seconds out of 9. You know, that's almost a third of the CPU time increase because of the contention from the other work. Let me try this now, code 203. One of the key things we're trying to do here, let me actually put it in a file. The purpose of the sched yield is to give the CPU up, but there's nothing to give it up to, so it goes right back to the same OpenMP application that does another sched yield. It is thrashing on sched yield and synchronization right now. But the single-threaded version, if the sched yields are working correctly, it ought to be able to get to these. And there we can see the code 203 is running. Look at my CPU utilization went up. So it had something to give it to. But I still have high system time running there. Okay, I want to do one thing here and see if this is going to make a difference. sysctl-a rep for yield, sysctl-w, kernel.sched underscore compat underscore yield equals 1. I advise having that set to a 1. Okay, we didn't really catch it. Our work is starting to finish now. So let me try that again now. I still have the code 2MP running multi-threaded. All those single-threaded versions got through the system faster than the multi-threaded version. It's still running. Let me fire it off again. Let me actually get a larger window here. Oh, there we can actually see now, 100%. But I'm trying to prove why not to run things wide open. And if I go back to this one here, set that back to a 0. Kind of hard to compare because all those code 2s are finishing, so let me fire them off again. So again, the purpose of the sched yield, all that system time was context switching. A perf top would prove that. Oops. Oh, we got sealant at the top of the list because of the single-threaded, but look at all the thread return. CPU scheduler, synchronization. Now let me try writing and changing that value again back to a 1. And you will see that it immediately went to 100% CPU utilization because now that sched yield is working correctly. But again, before with this red, it was doing sched yields, but there was nothing to sched yield to. So it was thrashing on sched yield. It'd say, are you done? Are you done? No. Give up the CPU, but then the kernel would throw it right back to me and say, wait a second, I don't want it. Sched yield again. In IRIX days, we had an SGI NAP where we could pass into the parameter, the system called how long to keep it away from me. So when you did a sched yield, you say, don't give it back to me. Give it to somebody else. Okay. Okay, so where are we on this? I kind of wanted to take a little break here and then come back to MPI. That work for everyone?
Okay.
So we got an OpenMP application. We were profiling it. We were seeing the effect of the synchronization events. We were not able to actually get this code down less than 8 seconds yet. And I don't know that we will because this code was not written for a multi-threaded situation. It's a 40-year-old code or 35-year-old code. So let's come back on the hour, and then we'll do MPI.
Okay.